children, for the next episode, we are discussing about electromagnetic induction. In our last class also, we discussed about electromagnetic induction, and in that how the electromagnetic induction takes place by using an activity coil, galvanometer and a bar magnet. We discussed how the process of electromagnetic induction takes place. See, in that we used coil, galvanometer and bar magnet. When we brought this bar magnet near to this coil, the magnetic flux, we know that this magnetic flux originated from north and it goes to the south. These field lines. When we brought into this coil, this bar magnet, there is a magnetic flux variation. There will take place a magnetic flux changes. This flux changes induce an EMF in the coil, and that EMF is called induced EMF. So there will produce a current, and that current is called induced current, and that phenomena is called electromagnetic induction. Now we want to know if a current carrying coil can also induce a current when we place another coil nearby it. For that, take two insulated copper wire coil which are wound on a paper roll, and suppose this first coil which contains large number of turns, and to this we connect a battery and a key, and this coil is called primary coil. This coil is called primary coil, and the second coil there is, we connect a galvanometer now. Current passes through this primary coil. When we plug in this, observe, is there any changes in the galvanometer that is connected in the secondary coil? This primary and the secondary coil contain large number of turns. When we switch on or when we plug in the key, the current grows from 0 to maximum and it becomes steady in the primary. We know whenever current passes through a conductor, there will produce a magnetic field. When we plug in the coil, that means when we plug in this key and the current grows from 0 to maximum, that means when the current changes from 0 to maximum, there will produce a magnetic field. That magnetic field also grows from there is a change in the magnetic field because current here at first it was 0, now it is maximum or it is steady. Now the magnetic field also steady, but when the current goes from 0 to maximum, there is also a change in magnetic field. This secondary coil is placed in this magnetic field. This coil is a secondary coil. Now we can observe there is a deflection in the galvanometer for a moment. When the current becomes steady, there is no deflection. When the current in the primary coil becomes steady, there is no deflection in the galvanometer because now there is no change in the magnetic field, even though there is magnetic field, but no change. So there is no deflection. That is, this changing magnetic field can induce a current in this coil. Now we switch off or we take out the plug. Then what happened to current in the primary? Is the current remains there? No. Now the current in the primary coil becomes maximum to 0. Current in the primary coil changes from maximum to 0. When the current becomes 0, what happens to the magnetic field? Magnetic field also changes from maximum to a maximum value to 0 value. So there is a change in the magnetic field. That field again induces a current in the coil, so the galvanometer deflects again. So the galvanometer deflects again. That means by changing the current in one of the coil, an EMF is induced in the nearby coil. Whenever there is a change in the current, that can induce a current in another coil which is kept in the field, and this also called electromagnetic induction or mutual induction. This also we used to say as a mutual induction or electromagnetic induction. That means changing magnetic field can induce current. Changing magnetic field induce current. This is the principle used in electric generator. Whenever there is a change in magnetic field, that induces current, and based on this principle, but electric generator works. Electric generator works. Once again, how the electromagnetic induction takes place in this arrangement. Here, how many insulated copper wire coils are? There are two insulated copper wire coils. The first coil through which we passes current is called primary coil, and the other coil in which induced EMF is produced is called the secondary coil. When thus we can see current in the secondary coil, whenever there is a change in the current in the primary coil, that means when the current increases from 0 to maximum, or current decreases from maximum to 0, or the magnitude of the current in the coil primary, whenever there is a change, we can observe and induce the current in the secondary, and that phenomenon is called what is electromagnetic induction, and it is called what is electromagnetic induction. To find the direction of the induced current, we can use, let me say here, we use two coils to produce what is electric current from one coil to another. This principle also called what is mutual induction, and we use this in transformers. This principle is used in transformers. There also we used in two coils. One is primary and induction. Now we want to find out the direction in which induced current produced. In which direction induced current is producing. For that we use Hmcs. Right hand rule. We use what is the right hand rule? We use Hmcs right hand rule. This rule says that suppose in our right hand, these are the forefinger, thumb, and middle finger. These are held at right angles to each other. That is mutually perpendicular to each other. If forefinger represents direction of the magnetic field, thumb the direction of motion of the conductor, then the middle finger represents direction of the current, direction of the induced current. That is held forefinger, middle finger and thumb in mutually perpendicular direction. If forefinger represents what is the field, thumb represents the direction of motion, then middle finger represents the direction of the induced current, In this way we can find out the direction of the induced current when a conductor moves in the magnetic field. That is how we can change the magnetic field within a conductor means either by changing or moving the conductor within the magnetic field, or keep the conductor in the magnetic field and move the magnet. Then also there will be a change in the magnetic field. Now, based on this, there are some questions given. Let us discuss. Explain different ways to induce current in a coil. The question is that explain different ways to induce current in a coil. What are the different ways that we can use to induce current in a coil? One method is to move the magnet towards the coil or away from the coil so that there is a change in the flux. And another method is to keep the coil at rest. One method is that keep the coil at rest, move the magnet so that the flux can change. Another method is that keep the coil and current through the other coil is changing, then also there will change in the magnetic field, so we can produce induced current. In these two ways we can produce current in the coil. Now, here are some questions given in our exercise. The first one, which of the following correctly describes the magnetic field near a long straight wire? See, we know magnetic field through a current carrying conductor can be find out using what is right hand grip rule. If the thumb shows the direction of current, then the fingers encircling the conductor shows the direction of the magnetic field. So the answer here given, the field consists of concentric circles centered on the wire. First one answer is D. The field consists of concentric circles centered on the wire. That means the wire is the center and concentric circles forms the magnetic field. Question number 2 from page number 240. The phenomenon of electromagnetic induction is. The phenomenon of electromagnetic induction is, here answer is C, producing induced current in a coil due to relative motion between magnet and the coil. The phenomenon of electromagnetic induction is, what is actually? Producing induced current in a coil due to relative motion between magnet and the coil. Question number 3rd one. The device used for producing electric current is called. Which device is used for producing electric current? Electric generator. What is called? Electric generator. Then 4th question. The essential difference between an AC generator and a DC generator is AC generator has slip rings while the DC generator has a commutator. Question number 4, answer D. AC generator has slip rings while the DC generator has a commutator. Question number 5. At the time of short circuit, the current in the circuit increases heavily. At the time of short circuit, current in the circuit increases heavily. That means in a large amount. Question number 6. State whether the following statements are true or false. State whether the following statements are true or false. A. An electric motor converts mechanical energy into electric energy. But actually, it's false. An electric motor converts mechanical energy into electrical energy. But actually, what is happening? It converts electrical energy into mechanical energy. Electrical energy into mechanical energy. So, the given statement here is false. And question B. An electric generator works on the principle of electromagnetic induction. Electric generator works on the principle of electromagnetic induction. It is true. Next is C. The field at the center of a long circular coil carrying current will be parallel straight lines. It is correct. That means inside the solenoid, magnetic field lines are parallel. That means uniform. So B and C, these two are true. And D. A wire with a green insulation is usually the live wire of an electric supply. In a household wiring, we use a red wire for live wire. And green wire is used for earthing. Green wire is actually used for earthing. Now question number 7th one. List 2 methods for producing magnetic fields. Which are the 2 methods we can use for producing magnetic field? One, by using current. That means when current passes through a conductor, there will produce magnetic field. Or that means that method is used in electromagnet. Another one method is using permanent magnet. A permanent magnet also can produce a magnetic field. Now, question number 8 one. How does a solenoid behave like a magnet? Can you determine the north and south poles of a current carrying solenoid with the help of bar magnet? Explain. How does a solenoid behaves like a magnet? A solenoid behaves like a current carrying solenoid behaves like a bar magnet. A current carrying solenoid behaves like a That means its opponent, if the current is here clockwise, here it is in anti-clockwise, then if the current is in clockwise, then this end is south and this end will become north. So magnetic field lines originate in this manner. From this, a current carrying solenoid, its properties like that of a bar magnet. Its one end is north pole and the other end is south pole. The end at which current flows in clockwise, that is south pole. The other end which current flows in anti-clockwise, that end is north pole. These poles we can determine by using a bar magnet. If one end of the solenoid attracts south pole of the bar magnet, then that end is north. Otherwise, if south pole of a bar magnet is repelled by one end of a solenoid, then that end is south. In that way we can find out the north and the south poles of the solenoid. Next, question number 9 when is the force experienced by a current carrying conductor placed in a magnetic field largest? Question number 9, when is the force experienced by a current carrying conductor placed in the magnetic field is largest? That means current carrying conductor is when the direction of current is at right angles to the direction of the magnetic field, then the force becomes largest. That means field and current. This is the direction of field. This is the direction of current. If they are at right angles, then that means current is perpendicular to the field. Then the force is maximum. Now, imagine that you are sitting in a chamber with your back on the wall, an electron beam moving horizontally from back wall towards the front wall is reflected by strong magnetic field to your right side, which is the direction of the magnetic field. See, imagine that you are sitting in a chamber, your back on the wall, an electron beam moving horizontally from back to forth. That means electron beam is from back to forth. That means current is in this direction. See, current is in this direction. Then, what is saying? An electron beam is moving horizontally from back wall towards the front wall, is reflected by a strong magnetic field to your right side. That means magnetic field is the right side. What is the that means directional deflection. That means the force is acting in this direction. Current is in this direction. Then which is the direction of the magnetic field? That we want to find out. That means here the electron beam is current towards us. In this way, current towards us. Direction of the field. Then what will be? This is the right side. In this direction, force. Then field is in the upward direction. That will come. Then question number 11. Draw a labeled diagram of electric motor. Draw a labeled diagram of electric motor. Explain its principle and working. What is the function of splittering in an electric motor? That means labeled diagram of electric motor is this figure we want to draw. Here, field magnet, what actually it does? This field magnet provide magnetic field. This is the armature. A, B, C, D is a rectangular armature. That means when current flows through this one, that means the current flows through this armature, there will produce a force and it rotates in the anti-clockwise direction. That means force in the arm AB and CD are opposite. So that force are equal, but they are opposite. So it will produce a turning effect. So it rotates. This split rings provides, that means here the split rings, actually what is the function of split ring? That means every half rotation, it changes the direction of current, hence it helps to rotate the motor always in the same direction. That means motor will rotate always in the same direction, which is in the anti-clockwise direction. Here the motor will rotate. Main parts of the electric motor are field magnet, armature, split rings. It is also called a split ring commutator because that split ring changes the direction of current after every half rotation. So it is called a split ring commutator, then brushes. Now, so the question answer is over. Once again the same question. Draw a label diagram of an electric explain its principle. Its principle means a current carrying conductor, if it can move, when it is placed in a magnetic field, a force is acting on it and that will move in the direction of force. A current carrying conductor placed in a magnetic field will experience a force and it moves in the direction of force. That is the principle of electric motor. What is the function of split ring in the electric motor that I discussed already? Name some device in which electric motors are used. Some names we got give where we use electric motor. We know in electric fan, mixer, that means mixer grinder, and also in computer, and device like electric motor, that means which we used to pump water. There are we use this electric motor. Name some device in which electric motors are used, where we use in the case of what is computer, then electric fan, electric motor, then a mixer, that means electric mixer. There also we use this electric motor. Now question number 13. A coil of insulated copper wire is connected to a galvanometer. A coil of insulated copper wire is connected to a galvanometer. What will happen if the bar magnet is pushed into the coil? When the bar magnet is pushed into the coil, the magnetic flux linked to the coil changes. So an EMF is induced in it and the current produced we can notice with the help of galvanometer. That is, galvanometer shows a deflection, it means a current is produced in the coil. Withdrawn from inside the coil. When we taken out the magnet from the coil, then also there is a change in the magnetic field. So a current is induced in the coil and that current is shown by the galvanometer. So the galvanometer deflected, but that deflection is opposite to that of the that we noticed in the previous case. Held stationary inside the coil. When we keep the magnet inside the coil, there is magnetic field, but there is no change, hence no current is induced in the coil, hence the galvanometer shows no deflection. There is no induced current, so the galvanometer does not show any deflection in that case. Now question number 14, the two circular coils A and B are placed close to each other. Two circular coils A and B, this one coil, this another coil, A and B. Two circular coils A and B are placed close to each other. If the current in the coil A is changed, suppose if the current in the coil A is changed, how we can change? When we plug in the key, current is changing, or when we take out the key, then also there is change in the current. See, a coil of insulated, two circular coils A and B are placed close to each other. If the current in the coil A is changed, will some current is induced in the coil B? Give a reason. Now, if there is any current is induced in this coil, suppose if there to find the current, we connected it to a galvanometer. Answer is what is yes. Some current is induced when there is change in the current in this coil. There is a change of magnetic field when the current in the primary coil or first coil changes. There is a magnetic field is changes. That magnetic field changes also induce a current in the secondary coil. So that shows a deflection. That means whenever there is a change in the magnetic field, a coil or second coil placed in that field, there will be a change in the current, or there will be a change in the magnetic field, and that magnetic field will induce a current. So that current deflects the galvanometer. Question number 15. State the rule to determine the direction of magnetic field produced by the straight conductor carrying current. Which rule? That means the right hand grip rule is using to find the direction of current in this way. Thumb points the direction of current, then the fingers encircling the conductor shows the direction of current. Second, force experienced by a current carrying straight conductor placed in the magnetic field perpendicular to it. Force acting on a current carrying straight conductor placed in a magnetic field, we can use Fleming's left hand rule. Which rule? We can use Fleming's left hand rule to find the direction of force acting on a straight conductor which carry current when it is placed in the magnetic field. And next one, third question, current induced in a coil due to its rotation in a magnetic field. Current induced in a coil due to its rotation in a magnetic field. That is, in which direction magnetic field, in which direction is the current induced in a coil when it is placed in the magnetic field. We can use Fleming's right hand rule. We can use what? Fleming's right hand rule to find the direction of current in that case. Now, question number 16 on, explain the underlying principle and working of an electric generator by drawing a labeled diagram. What is the function of brushes? Here this question is mainly not in our syllabus. Then also working principle of electric generator is electromagnetic induction. Electromagnetic induction. The brush is a conductor that supplies current to the external circuit. That means the brush is in contact with the armature that supplies current to the outer circuit. When does an electric short circuit occur? When does electric short circuit occur? Whenever there is two main line touches, or when we draw too much current from the circuit, or when we take out over current from a single plug. In that case, current becomes heavy. So in that case, there is over current. Due to over current, there is a short circuiting happening. What is the function of an earth wire? Why is it necessary to earth metallic appliance? Function of earth wire is to earth the metallic part of the appliance. Which part? To earthing metallic part of the appliance. For that purpose we use earth wire. Why we connecting or why we earthing metallic part of appliance means if there is any insulation failure, then current can enter into the metallic part, and if any person touches it, then he can get electric shock. If the metallic part is earthed, then if there is an insulation failure, then current from the main line enter to the earth wire, and due to over current, but electric fuse may go, then there we can avoid electric shock. For that purpose we use what is earthing in the metallic part. With this all, we can complete these all questions which is given in the exercise. So what are the things you want to remember from this unit mainly? From this unit we mainly discussed first of all, when current is passed through or whenever current is passed through a conductor, a magnetic field is produced, and that magnetic field we can find out the direction of the magnetic field we can find out by using a right hand grip rod. Then we discuss about how that magnetic field related to the distance from the conductor. Magnetic field is inversely proportional to distance. Then current carrying conductor, when it is in the form of a circular loop, how is the magnetic field? At its center, the magnetic field lines becomes straight. Then how the magnetic field produced in a solenoid, it is just like that of a bar magnet. Then also we discuss about how we can find out the poles at the ends of the solenoid. Then we discuss about what happens a current carrying conductor placed in the magnetic field, is it experience a force or not? We discussed that that will experience a force. Then working principle of electric motor. Then we discuss about what is actually electromagnetic induction, what is actually electromagnetic induction. Then Fleming's left hand rule. Then Fleming's right hand rule. Then about our questions that given in our chapter, in this chapter. With this all, we can wind up this class. Okay, thank you.